So we were talking about the generalized Hooke's law, and we had actually looked at this equation already. And this is a fourth order tensor and has 81 components. It's a fourth order tensor. So now a few things are easy to see here, that not all of these 81 components can be independent. For example, I know that sigma ij is equal to sigma ji by the balance of linear momentum. The balance of angular momentum. So I must have sigma ji equal to sigma ji kl epsilon kl equal to sigma ij, which isCijkl epsilon kl, which can only be possible if these two things, this and this, are the same. So I must haveCijkl equal to Cjikl out of these 81. So some of these, because of the symmetry of the stress tensor, some of these 81 constants would not be independent. If I specify one set, the other set would also get specified. Similarly, I know that epsilon kl is also a symmetric tensor. So sigma ij is equal toCijkl. Epsilon kl would also be equal toCijlk epsilon lk. So this is also possible ifCijkl is equal toCijlk. So again, this would reduce the numbers from 81 to a smaller number. So that is what is written here, that it will have these following symmetries. It will have these symmetries, which follows from the symmetry of the sigma ij and epsilon kl. Now, if we take these symmetries into account, then we will see that these 81 constants come down to 36 independent constants because of the symmetry of sigma ij and epsilon kl. So these are called minor symmetries, and minor symmetries bring down the number of components from 81 to 36. Now, sometimes with this minor symmetry, we choose to write this 36 components as a 6 cross 6 matrix. And this is quite common. This will be used quite a bit. And to do that, we use something called a Voigt notation. So we change from the index notation to what is known as a Voigt notation. In order to change to the Voigt notation, you have to be actually careful. You have to do it by hand yourself. What it depends on is a kind of mapping that you decide a priori. For example, I have decided that all 1 cases will be mapped to 1, 2 will be mapped to 2, 3 will be mapped to 3, 1 2 and 2 1 cases will be mapped to 4. Remember, 1 2 and 2 1 are, because of the minor symmetries, they're always the same. 2 3 3 2 will be mapped to 5, and 3 1 1 3 is mapped to 6. Many books follow a different order. So mostly they differ in these three components. In most books, 1 1 2 2 and 3 3 are mapped to 1 2 3, and then how the unequal components are mapped differs from book to book. So I will use this 1 2 to 4, 2 3 to 5, and 3 1 to 6. And once I do this, I can write this, write theCijkls. I can write theCijkls as a 6 cross 6 matrix with components CAB, where A is the mapping of IJ maps to A and KL maps to B according to this rule that I have a priori decided and I'm going to stick to. If I do that, this is how the mapping will look like. So C11, so for the CAB, C11 is where IJ maps to 1 and KL maps to 1 as well. So C11 is C1111 of the tensor component. Similarly, C1122 maps to C12 because 1 maps to 1, 2 maps to 2. This is C13, 1 maps to 1, 3 maps to 3. This is C12 because so this is C14 because 1 maps to 1 and 1 maps to 4. This is 15, this is 16. So this is all according to this mapping. You can take any arbitrary one. You can take this one. This 1 2 maps to 4 and 2 3 maps to 5. So this is your C45. This is your C45. And that is how I have written the 6x6 matrix. The 6x6 matrix is symmetric. So there are 36 36 components here, and these contain all the independent components of C, which are determined after taking the symmetry of sigma ij and epsilon kl into account. Now let us change gears a bit and look at a concept that we have briefly alluded to before but have not looked at in detail. That is the concept of the strain energy density function. So from thermodynamics, which we are not going to deal with here, thermodynamics of deforming bodies, you can postulate that there exists a scalar function. So this is a scalar function of a tensor, that is epsilon ij. This is a scalar function called the strain energy density function with units of energy per unit volume. So this is units of energy per unit volume. This scalar function is such that if you take its derivative with respect to epsilon ij, you get sigma ij. If such a scalar function exists and we know it, then this material is called hyperelastic. So a hyperelastic material has a strain energy density function whose derivative with respect to strains gives you the stresses. So this is actually another way of stating your constitutive equation. So for a linear material, for example, we know that the constitutive equation is stated in terms of the generalized Hooke's law as this, where these are constants. So we can imagine that this phi would be a quadratic function of the strains, so that taking its derivative with respect to strains would give you a linear function of strain, and the constitutive equation is indeed a linear function. So stating this for a hyperelastic material, is completely equivalent to stating the constitutive equation. Why do we state it in this particular way? Is because we are not always only dealing with linear elastic materials. So it is not necessary that phi would always be a quadratic function of strain. Phi can be some other function of strain, and indeed for materials which do not obey linear elasticity, which are non-linearly elastic, for example rubbers and very soft materials like tissues and so on, biological tissues and so on, do have strain energy density functions which are not quadratic functions of strain. However, in this course, since we are dealing with linear elasticity only, we will only consider cases where phi is a quadratic function of strain. And the existence of phi from thermodynamics is guaranteed in cases where the material is completely reversible and the loading and unloading paths are completely on top of each other. So if you plot a loading path in a stress strain plot and you unload from a particular stress, you would follow the same path while loading and unloading. So completely reversible path independent deformations can always be, from a thermodynamic point of view, can always be shown to have a strain energy density function which is a scalar function of strains, and which we will denote by phi. So this kind of an equation is for a general nonlinear elastic material, valid for a general nonlinear elastic material as well, but we will concentrate only on the case of linear elastic materials, for which phi would be a quadratic function of strains. Now, once we take into account the fact that phi exists for a reversible path independent material, of course, a linear elastic material is a special case of a reversible path independent material. Once we accept its existence, then there are simple things that we can show. As I was saying, that sigma ij is given by del phi del epsilon ij, but we also know from generalized Hooke's law that it is given as ij mn epsilon mn. So both of these are completely equivalent ways of stating it. I can either state a quadratic function for phi in strains, or I can state this straight away. Would be completely equivalent. Now take the derivative of sigma ij once again, now with respect to, not with respect to epsilon ij, but with respect to epsilon kl. If you do that, then from epsilon mn you will get km, delta km, that is m and k, and delta ln. The deltas will knock off m and n, so you will get Cij kl. So the second derivative of phi for a linear elastic material would give you Cij kl. Obviously, if I started from the other way around, so I took ij first, so I wrote sigma kl, that would be del phi del epsilon kl according to the thermodynamic principle, and this would be equal to, let's say, C kl mn epsilon mn from the generalized Hooke's law. So this derivative must give me this for a linear elastic material, because this is a quadratic function. Now take the derivative once more, now with respect to epsilon ij. So I'll take del square phi del epsilon kl del epsilon ij. So that would give me C k l m n delta I m delta j n, oops, delta j n, which will knock off m and n, so I'll have k l I j. Okay, so this is what I will get if I had started with sigma kl instead of sigma ij. But I know that if I look at this quantity and this quantity, as long as phi is a continuous function in strains, then I know that the order in which I take the derivative does not matter. So in other words, del square phi epsilon ij epsilon kl is same as del square phi epsilon kl epsilon ij. So I have this equation. This leads to Cij kl. This leads to Ckl So the existence of this scalar strain energy density function, which is an outcome of thermodynamics of deforming bodies, elastic deforming bodies, tells me that Cij not only has minor symmetries, so we already have seen these minor symmetries, Cij Cji and Cij equal to Cij These are minor symmetries that come from the symmetry of the stress and strain tensors and bring down the number of independent constants from 81 to 36. On top of that, we have what is known as a major symmetry. So we have Cij equal to Cklij. This is a major symmetry. These are minor. And this is a major symmetry. And this will further reduce the number of independent elastic constants that we will have. So even if we have done nothing, we have made no assumptions about the material, we now know that because just because the stress tensor is symmetric, we should have this. Just because the strain tensor is symmetric, we should have this. And just because thermodynamics dictates that phi should exist, we should have this major symmetry. Which basically, if we go back to this matrix representation, will tell us that okay, C1122 and C2211 must be the same, C1133, 3311 must be the same, C2212 and C1222 must be the same, which means that we must have a symmetry of this part. So we should have now how many? We have 36 because of minor symmetries, and now we have um, 18 plus 3, which is 21. So uh, in the even without considering the material nature of the material at all, we can show that minor symmetries and major symmetries bring down the number of independent constants in the Hooke's law, in the generalized Hooke's law, from 81 to 21. Okay, but that's it. 21 is what you will have to determine, and 21 still is a large number. So 21 is still a large number. A lot of experiments will be needed for every material to determine this 21 constants. So now let us bring in the material here. So can we use certain properties, certain symmetries in the material to reduce this even further? Is that possible? It turns out that it is very well possible to bring it down if we take certain symmetries of the material into account. So now the man-made arguments come into the picture. Okay, so there are different kinds of materials. I don't know how much of material science you have learned, but there are materials with, for example, which are called triclinic materials. So think of a single crystal of a triclinic material, and a triclinic material has a crystal structure which looks like this, where alpha, beta, gamma. So these are atoms, for example. So these are atoms of the triclinic system, and alpha, beta, gamma are not equal, and neither are they equal to 90 degrees. A, B, C are also not equal. So this is a rhombohedron. If you, I don't know whether that's a correct word, but you know what I mean. It's a rhombus and forms some kind of an hedron. And the only symmetry that it has is about this plane. What I mean by that is, if you rotate it by 180 degrees, you will not be able to distinguish between the rotated unit cell, this is the unit cell. You will not be able to distinguish between the rotated unit cell and the unrotated one. So that's the only possible rotation that you can have of this unit cell that will uh, that will that will result in a indistinguishable system. So just think of a system which is made up of a crystal formed by unit cells of this rhombohedrons, and this will have just one single plane of symmetry. So at every point in the body, when you think of this as a continuum, you don't see the unit cells anymore, but the unit cells are there at the background. So at every point on the continuum, you will have one plane of symmetry. You will have just one single plane of symmetry, and that plane will coincide with this plane of the rhombohedron. For a material with this kind of a symmetry, where there is only one plane of symmetry, we call that a monoclinic material. So we call that symmetry monoclinic symmetry. So you have this one plane of symmetry on which these rhombohedrals are sitting like this. Okay, and there are millions of them on this plane. Obviously, we don't see them. What we see is that there's this one plane of symmetry about which, if I take an axis x1, x2, x3, or take an axis x1 bar, x2 bar, x3 bar, I will not be able to distinguish between the two, because this is a plane of symmetry, which means that when I transform my um, constitutive matrix, the Hooke's law, CIGKL, when I transform it from this coordinate system, this is my old coordinate system, to this coordinate system, a new coordinate system, I should get the same constants, because I should not be able to distinguish between the sets of constants if I make a reflection transformation about a plane of symmetry. That's the idea here. And remember that Q is an orthogonal tensor with det Q equal to 1 for rotations and -1 for reflections. This is a reflection operation that we are doing, and about a plane of symmetry. So when we do this for monoclinic symmetry, where there is only one plane of symmetry in the material, this is how it should be. So the Q in this case obviously is easy to determine. So x1 and x1 bar are the same, so the angle between them is 0. Cos 0 is 1, x2, x2 bar 1, and x3, x3 bar, the angle between them is pi, and cos pi is -1. So this is going to be just a diagonal matrix with 1, 1, -1 along the diagonal. And then if I do this transformation according to this transformation matrix, if I convert the components of the Hooke's law CIGKL to the new coordinate system, I should get the same sets of numbers. I should get the same sets of numbers, because this is a rotation of axis about a plane of symmetry. Okay. Now let us look at, say, one case. Say let us look at C1111 in the old system, that is x1, x2, x3 system, and how it converts to in the new system. So if you do it for 1111, so you put 1111 here. So C bar 1111 will be Q1P, Q1Q, Q1R, Q1S, and CPQRS. And now if you look at the Q, the only way this can be non-zero is if PQRS are all equal to 1. So so in that case, it will give you C bar 1111 is equal to C1111, which is what we wanted. We don't want this to change the this being a transformation, this being a reflection transformation about a plane of symmetry. We don't want it to change. So we do want C bar 1111 to be equal to C11, and that is what we get. So if we do it for 1122, 2222, 1112, etc., we'll also see that we will satisfy the condition that this transformation here should not change the components. Now let us look at a case where we do transformation for C1113. So we want to find out C bar 1113, which should be equal to C1113, because it's a transformation about a symmetry plane. So now we have Q1P, 1Q, 1R, 3S, and the only way this can be non-zero is if PQR are equal to 1 and S is equal to -1. That's the only way in which it can be non-zero. So if you go back here, this is 1, this is 1, this is 1, and this is -1. So you will have C bar 1113 equal to minus C bar 1113. But because you are doing a transformation about a plane of symmetry, these two should be equal. So the only way this can happen is if both are equal to to 0. So having one plane of symmetry, would make certain would force you to the conclusion that certain components of CIJKL will turn out to be 0. These are components like this, and if you look at it a little more carefully, you will see that these are components in which 3, about which the reflection takes place, which is a plane of symmetry. X3 gives you the plane of symmetry. So wherever 3 appears an odd number of times in the indices, all those components are going to be 0. And if you write it in the Voigt notation, the matrix form, the symmetric 6 cross 6 tensor, you'll see that these components, you can check them out, these components will turn out to be 0. These components will not turn out to be 0. These have 3 2 times, here, here, here as well, here it has 4 times. So these components will not turn out to be 0, but these components will turn out to be 0, and this reduces the number of constants from 21 to 13. So for a monoclinic material, if we have just one plane of symmetry, then and that plane in our case is the x3 3 plane, but it can be any other plane. So depending on which plane is the symmetry plane, you have to set the corresponding components to 0. You will finally have 13 components to determine. Now, monoclinic is not a very common material. What is a more common material, and various natural materials and man-made materials, synthetic materials like composites do have this character, is known as orthotropy. So orthotropy is a case where you have not one plane of symmetry in the material, but 3 planes of symmetry, which means that this is the first plane of symmetry. So if you reverse the x3 axis, the components of CIJKL remain the same. The material does not know that you have reversed the axis. There's no effect. Similarly, if you reverse the 1 and 2 directions, so if you take this plane where you have reversed the 1 direction, or this plane where you have reversed the 2 direction, the material doesn't get to know. So, so this is called an orthotropic material, and many composites are orthotropic. They're made that way, and as a result of orthotropic symmetry, you can imagine what will happen. It's like applying the monoclinic symmetry 3 times. So what you are doing, what we were doing for the monoclinic symmetry was, when there was monoclinic symmetry about the x3 axis, we were saying that if 3 appears an odd number of times in the indices, then those components will turn out to be 0. Now we have to say that if 1 appears an odd number of times, or 2 appears an odd number of times, those components also are going to be 0. So you can apply the trick of the previous slide in this as well, and you will see that now several other terms will turn out to be 0, and this will be the shape. These terms will turn out to be 0, and this will be the shape of the matrix form of the CIJKL. Now just I had this small picture here. Wood is a very common natural material which has orthotropic symmetry, and in wood, if you cut a log, you see these things which are called annular rings. These are annular rings, and these annular rings are rings that grow. One of them grow in per year. So basically, if you count the number of rings along the cross section of a tree trunk, you would be able to gauge its age. Now, a plank that is cut out like this will have So these annular rings are actually strong fibers that are running along the length of the log. So if you cut out this plank here, so this plank goes like this. It's a long plank. So this plank will have roughly have orthotropic symmetry. So there would be one set of properties perpendicular, one set of properties along the fiber direction, and one set of properties in the out of the fiber direction, one set of properties in the tangential direction. So it will have these three planes of symmetry. So if you flip about any of these axes, if you flip the axis about any of these, the properties should be the same. Properties should be the same. This is for wood, which is a natural material. There are synthetic man-made materials like composites that also have orthotropic symmetry. And in case of orthotropic symmetry, you have further reduction in the number of independent constants, and there are only 9 constants here. A very special case of orthotropic symmetry occurs in materials, again natural materials as well as man-made materials, is known as transversely isotropic material, transverse isotropy. Uh, so in an orthotropic situation, a rotation about the x3, rotation about x2, or rotation about x1. So this is rotation about x1, and this is about x2, and this is about x3. And these three rotations did not change the components of the stiffness matrix, and that led us to the conclusion that the number of independent components should be 9. Now, in transversely isotropic material, we have the additional thing that a rotation of the axis in the x1, x2 plane, rotation of the axis in the x1, x2 plane also does not change the components of CIJKL. So if you take the axis and rotate it about the x3 axis, so that you are rotating it in the x1, x2 plane, this is the rotation tensor. This is the rotation tensor. This is the Q that you will get if you do a rotation of the x3 axis along on the x1, x2 plane by some arbitrary angle theta. So no matter what the value of theta is, as long as you are rotating the axis in the x1, x2 plane, the symmetry is such that the material does not know that material does not know that you have rotated the axis, in the sense that the CIJKL components do not change due to this rotation. In this case, the independent constants come down to even lower values, and this is the form of the stiffness matrix. So I should put C here. So this is the form of the stiffness matrix that you are going to get for a transversely isotropic case. Again, many man-made materials, for example, unidirectional fiber reinforced composites. So this gray area is a polymer, which is and this these blue things are fibers. So these are very strong fibers, Kevlar fibers, for example, bulletproof jackets, or many parts in aircraft are made in this way. So these are strong fibers embedded in relatively softer polymer matrix. So these fibers are very strong. So this material is very strong in this direction. However, in this plane, if you rotate the axis, the properties are more or less the same, and therefore this is a man-made example of a transversely isotropic material. A natural example are rocks called sedimentary rocks, and an example of that is a rock called shale, which is a sedimentary rock in the sense that it grows by, so across the thickness of this is called the thickness direction is called a bedding direction of this rock, and it grows by deposition of silt on, say, dried riverbeds or dried seabeds. So one layer of silt deposits, and then another layer, and then another layer, and another layer, and this happens over millions of years. So one layer each deposits, and then there's a big deposition that happens on the top, which puts a lot of pressure and compacts this. And when that happens, um, this direction becomes your transverse isotropic direction. This direction in our notation becomes a three direction. So the bedding is taking place in this. This is the direction in which the silt is being deposited over years. But if you look at in the in plane direction, which is this, if you look at in the in plane direction, it's more or less the same in all directions.